Yeah, today we're talking about a ChipDSC and the thermal analysis in food industry, especially. So I'm Michael. I'm product specialist for calorimetry here at Linsights, and yeah, I'm here since 2017. And if you want to connect with me, feel free to find me on LinkedIn, write me a mail or give me a call. You can find the number here. And yeah, so we are Linsights. And so Linsigh's Messgeräte was founded by Dr. Maximilian Linsighs here in Selb, based in Germany. And we still manufacture in Selb with our own sales and service locations, also in USA and China. But of course, we have much more traders worldwide. So whenever you're wondering who you want to ask, you can find all of them on our website here. And what are we doing? So we do thermal analysis and build the devices for that. So there's a broad range we cover here with our analyzers. So of course, the differential scanning calorimetry we want to talk about today. But there's also thermogravimetry and the combination of both the simultaneous thermal analysis, but also dilatometry, TMAs, thermal conductivity and thermal divisivity, and yeah, many more. For example, for Hall effect or thin films. So we cover a broad range here. And of course, you can find all of the informations about the devices online on our website, or don't hesitate to ask us if you're interested in any device. But as I mentioned, today we want to talk about calorimetry. So especially about differential scanning calorimetry with the Chip-DSC here, you can see in the upper left corner. So regarding the Chip-DSC, yeah, it's a quite special device. So why are the most DSCs, yeah, much bigger than the Chip-DSC? So we've changed something here for the device. So at the left side here, you can see the conventional layout. So a surrounding oven with the heater. And in the mid, you can see here the sample crucible with the sample inside and the reference may be filled with an inert material or not. So this depends on the application. And below these crucibles, you can find the thermal piles or the temperature sensors in general for the differential signal here. With Chip-DSC, yeah, we've changed that a bit to an vertical layout, not anymore an horizontal layout. So now we have our sample side on the top. Below, of course, the temperature sensor for the sample. And the heater is now not surrounding in the oven. It's now inside of our measurement cell of our sensor, our chip-based sensor here. And below, you can find the fixed reference side with its temperature sensor. So everything is within a ceramic monolith. You can see here the bottom left corner. So this is the Chip-DSC at all. And through this small design, we have also two layouts. So the smaller Chip-DSC 1 and 10, and the bigger device with some more opportunities here, the Chip-DSC 100. So again, here you can see the principle of the DSC with the heat flow at all. So the sample side and the reference side in a surrounding oven. So both measurement systems measure, of course, the heat flow, and the losses here are compensated through the simultaneous heating of sample and reference in the best way. And we are checking the difference between sample and reference. So if there's any endothermic or exothermic effect, we can see this in the differential signal here. Now again, for the Chip-DSC, here you can see the principle of a Chip-DSC sensor. Also here, of course, the heat flux, the heat flow is measured. But in this case, we have a fixed reference. It's heated by the same way like the sample. So for this reason, this measurement device works. and everything is inside this ceramic monolith produced by a thick film technique as a manufacturing method. So what could we see with our ChipDSC? Of course, everything you can see with a conventional DSC. So this is just an example, in this case, a polymer. So of course, you can see the glass transition with hysteresis peak, maybe some overlapping effects here in our measurement, the cold crystallization, a melting, and on the one hand, if there's some oxygen, you can see the oxidation, or if there's, for example, nitrogen atmosphere, the thermal degradation. So this is the heating run, and the cooling run, of course, you can see the crystallization and also the glass transition here. So that's it, basically. Another special thing we've invented last year is there are different sensors here for our ChipDSC. So we have the low mass sensor you can see here. So it's the smallest sensor with the best time constant here for the ChipDSC. And yeah, it's pretty small, and yeah, the lowest mass we can achieve here for really fast transitions and so on. Also, we have the standard sensor that covers the most application in a good way, but for especially for glass transition TGs, we have the high sensitivity sensor that delivers 30 up to 40% more signal here. So it's not that fast in comparison to the low mass sensor or the standard sensor, but especially for TGs and small effects, that's the perfect choice here. All of these sensors are compatible with your ChipDSC, so it doesn't matter if it's a ChipDSC 1, 10, or 100. All of them could be used and could be exchanged by the user itself. You just have to recalibrate or load an old calibration for the sensor, and then it works with this different measurement system. But yeah, today we want to talk about food industries and thermal analysis. This was just a short lookout about the device we are using here. So the food industries, it's more complex system with many components here, and of course through storage, through production, there are some cooling and heating runs while processing. And so the DSC is quite a powerful tool, I think, here in food industries for quality control, but also for troubleshooting and research, because of course you want to know the behavior, for example, for the melting of your fats or whatever. And yeah, an additional thing here is we can use optional equipment, of course, and for ChipDSC, it's quite easy to adapt these because of this open design. So it's no problem to adapt an UV curing option here. I can show you on the next slide, maybe better. We have UV curing, we have Raman spectrometers, we have camera options, of course, also different cooling options with intracoolers, Peltier elements, or liquid nitrogen. But there's also high pressure vacuum possible, or for quality control, maybe an auto sampler. All of them are compatible with the ChipDSC, and so I think, yeah, it's quite easy to find the right setup for almost every application here. And yeah, so maybe let's start just with some investigations here. I want to show you what's possible with the ChipDSC, and maybe you get some ideas what you can use for this DSC. And so we've started with butter and margarine. And so the measurement conditions here, we've used at all the ChipDSC 10 here. And what we want to know is, what about water content and the fats composition? Is it possible to separate them clearly or not? So for this reason, we bought 3 different margarines and a butter and measured all of them in our aluminum standard crucible. The sample mass was more or less 15 milligram for each. At a quite low heating rate of 5 Kelvin per minute. The purge gas simply was air, and But for this investigation, we need a cooling option, and so we were using the ChipDSC 10 for this reason. We've chosen the quench cooling option with liquid nitrogen. So this is now the result. What you can see here is we had some endothermic peaks. So first of all, of course, we can see the water peak. And if you're wondering why the enthalpy differs, of course, the water content is different here for each sample. And for this reason, and through this result, you can, for example, simply calculate what's the water content because you have the literature value for the enthalpy of melting water here. So also there are slight melting peaks of butter here at 35 degrees, and at 40 degrees, the low-fat margarine will begin to melt, and the fatty acids of plant and sunflower margarine melt at around about 50 degrees here. So this is what we received in this measurement. And sorry, this was too fast. Yeah, so to sum it up, it's really possible to distinguish the different samples here, the margarines and butter, through its composition. And yeah, it's also possible to figure out the water content of our sample and to get to know what about the fatty acids here in the sample itself. Yeah, quite similar, but not really the same is, for example, the chocolate. So we've measured different chocolate samples. Yeah, we've used 5 samples, I think. Yeah, here, 5 different chocolate samples. And yeah, so here we were interested on the melting behavior, the temperature, and of course the fat content. So also here we've used a ChipDSC 10 in combination with a quench cooler and liquid nitrogen in our standard crucible. In this case, we can use a higher heating rate of 20 Kelvin per minute because the peaks were broader at all. And also we've measured here under air. So the result you can see here on the right is, yeah, there are some difference for different chocolates. So chocolate at all is also just a mixture of fat, sugar, cacao, and emulsifiers. And what's important here for the manufacturer, for example, is what about a creamy feeling in our mouth, or what's the taste influenced by the melting behavior here? And so this really depends on here on the melting peak and the shape of the peak. So it's also important at room temperature how many fats are already molten or not. And what we can see here, there are different fats inside our chocolate. So almost everywhere we can see some double peaks caused by different fats. And what we can see here is, for example, milk fat causes the low temperature melting peak here at around about 18 degrees, or the plant fats causes higher temperature peaks. So to sum it up, the different samples show more or less splitted peaks. So it's, yeah, there are 2 peaks all the time here. And the more homogeneous the melting is, the better formed emulsion is. And so we can get an idea about the behavior and the taste of our chocolate by analyzing it through a ChipDSC and the DSC at all. And what's also important here, we can see it, especially for food industries, we often need a lower temperature, maybe not minus 100 degrees with liquid nitrogen, but a Peltier cooler to get to know the DSC signal at room temperature could be quite helpful here. So next thing is milk powder. So we had different samples of milk powders, and all of them should be tested for quality control because the humidity was quite important here, if it still can be used or not. And so in this case, we were investigating the TG, so the last transition of our sample here. And yeah, it was more or less always the same skimmed milk powder, but there were some differences between these samples. But what I want to show you here in the measurement on the next slide is it's really important to choose the right ambient conditions and the right measurement system here. So regarding the measurement itself, we also used the standard crucible here, around about 15 milligram for each sample, a heating rate of 10 Kelvin per minute, and for purge gas, we've used air, and as a cooling option, we were using the intracooler because in this case we've used the bigger device, the Chip-DSC 100, yeah, with some more cooling options. So this is the result now, and what we've done here is we've compared the standard sensor, our classic sensor layout, with our high sensitivity extended sensor layout. And what you can see there on the right is, yeah, there's a difference because due of the 30% higher sensitivity, we achieve much better signals here for this glass transition. So yeah, this is what we want to figure out here in this slide. Of course, it's possible to do the investigation also with the standard sensor layout. It's possible, but it's much easier if you use the extended sensor with a higher sensitivity. So you can see the results there. The glass point is quite comparable for two different samples. And yeah, as I mentioned, it's important to use the same ambient conditions here, so the same crucible, the same heating rate, and so on, to compare these measurements. And please don't wonder, if you check the y-axis here, I'm showing the DTA signal and not the enthalpy calibrated signal anymore, because of course, if we have an enthalpy calibration, the signal height would be the same between the classic and the extended sensor layout. Just the noise is smaller here in this case because the factor for the enthalpy calibration is smaller because the sensitivity of the extended sensor layout is much better. So this is just choosing to show you the possibilities here. And yeah, what's also important, so we cannot see it here, but we perform these measurements for heating rates between 5 and 400 Kelvin per minute. So the higher the heating rate is, also the higher the step height of our transition is, because the temperature gradient between reference and sample, of course, is higher if the heating rate is higher. But on the other hand, also the temperature of our glass transition is shifted due to higher heating rates. So as I mentioned, it's really important to choose the same measurement conditions here if you want to compare some samples. So yeah, I already told you this from this slide, I think. Yeah, just to sum it up, for TGs and so on, high sensitivity sensor is the perfect choice from my point of view. And TGs are sometimes better visible with a higher heating rate, but this is up to you to figure out if you should use a smaller or higher heating rate. Sometimes you have to fulfill a norm or something like this. So next thing is a coupling here. So we've measured alpha lactose, so also a part of milk powder at all. And yeah, there was an investigation. A customer was asking us, oh, we have a DSC signal here, but there's a strange behavior we cannot figure out. So if you have the possibility, can you do an investigation of this? And yes, so for this reason, we've used our Raman coupling, used Raman spectrometer by Wasage Photonics. And yeah, so over temperature, we were checking, okay, what about the Raman spectrometer? And we have a partner who's doing this all day long, and they do the evaluation. Unfortunately, I don't have it here, so I'm not allowed to show it, but at all, we can see it's possible to couple DSC, especially Chip-DSC, easily with a Raman spectrometer. And yeah, everything else is also quite standard. So purge gas was air, a heating rate of 10 Kelvin per minute. The sample mass of the lactose powder was around about 10 milligram in a standard crucible. Of course, in this case, we are not able to choose a closed crucible because we need the detection of our Raman spectrum. So this is the result here on the right side. This is the measurement from our customer, and yeah, so the last peak was quite strange, and they were wondering what happens there and for what reason. Yeah, can they see this? And on the left-hand side, you can see the Raman spectrum of lactose over a temperature range, and these were the data we've sent them, and so they were happy at all. So what we can prove here, it's really possible to check the phase changes related to temperature in combination of DSC and Raman spectroscopy. And so yeah, if you have a database or some further information about your material or Raman spectroscopy at all, this is a quite powerful tool for maybe some unknown effects or special happenings in your DSC signal. So yeah, one more, just more or less simple investigation is the investigation of starch, especially rice here. So we wanted to see the gelatinization of starch from different samples. So I've chosen 3 different rice samples just to compare them if they're more or less comparable, but the difference was the humidity. And so let's check if there's any influence here. The measurement device was the Chip-DSC 10 again, with a standard crucible with round about 12 milligram for each sample at a higher heating rate of 20 Kelvin per minute. By the way, if we have some faster samples or a higher temperature range, we are often using 50 Kelvin or 100 Kelvin per minute for our Chip-DSC here. But at these small temperature ranges, we are choosing smaller heating rates at all. The purge gas was air again, and also here we were using a quench cooling option with liquid nitrogen because we want some more baseline here before of our gelatinization peak. And at all, that's the result. So we had basmati rice, we had rice pudding grain, and the long grain rice with different humidity. And what we can see there, the peak maximum and the onset is quite the same, or almost the same. But the shape is really different for our different samples here. And this is caused by the humidity. And this is really affected, these peaks are really affected by the water content. But at all, they are comparable. So we've added, for example, potato here. So now in cyan and in green, you can see now potato. One of the samples is dried and the other one is a fresh potato. So now here we can see a huge difference between these 2 samples in comparison to our rice starch. And so even if you don't know what's the origin of your sample, it's possible to separate them by DSC at all and distinguish them. Of course, it's also possible not just the gelatinization could be discovered, but also the retrogradation. So everything about stalk so far. So one more, just a simple melting investigation here is oil. So we've used some plant oils here, and seven different types of plant oil were tested just to determine the difference of the melting behavior, to get an idea what about their behavior for melting here, because there are some further information and further investigations we can do on plant oils I will show you later. So we've used just a simple aluminum crucible with a smaller sample mass, just 3 small drops of our oil at a heating rate of 10 Kelvin per minute with a purge gas air, and quench cooling option with liquid nitrogen, and this is the result. So what we can see here is, yeah, these peaks are not that clear like indium, as you can see. So these are broader peaks and overlaying peaks we can see here, caused by different fatty acids. And what we also can see is sometimes the onset is a bit unclear because we don't know when does the first peak of does start, what's the onset temperature, and what's the second, and what should we investigate here. So for this reason, it's common practice sometimes to check the peak maximum here for this reason. But if you determine the peak maximum, please keep in mind the peak maximum is really dependent on the heating rate. So the onset temperature at all in theoretics isn't affected by the heating rate because the onset temperature is always the same, but the peak maximum is shifted with higher heating rates. So this is important. So the conditions are quite important here if you want to compare different samples. So what we can see here, if we are using a quench cooling option, cooling option at all, it could be helpful if you have broad peaks to get a more stable baseline in the beginning, and you're not directly starting with the melting peak here in this case. So for this reason, we were using the quench cooling option, especially for food industries. It could be quite helpful. And what's also visible, some of the oils are easily distinguishable, like for example sunflower oil and olive oil. So it's really easy to separate them here. But if you compare olive oil and peanut oil, they are quite similar. And so maybe we need some further investigation on this to get to know what about the origin of our oil here if we don't know what it is. What's also important, of course, if you measure oils and so on, it's possible to use an SFI crucible. So, for example, the oil doesn't crawl on the side of your crucible, and this could be really helpful. Otherwise, you will get some signals on your DSC signal you don't want to see because the sample contact differs a lot during heating. For SFI crucibles, the liquid is just placed in the middle of the crucible, and through its form, it's not able to crawl on the border of your crucible. So if you're interested in such crucibles at all, of course, don't hesitate to ask us. It's possible to order them. Also, if it's necessary for your investigation. But now I already told you I'm interested in some further investigations here, maybe. So another point we can determine or investigate in food industry is the oxidative stability. So in this case, there are different norms we can use here. So there are some ASTMs or some DIN ISO norms. In this case, I'm using the norm for plastics because, the first tests were performed with plastics here because food industry isn't just the food itself, but it's also important, for example, the packaging. What's about the your temperature range for your packaging? What's about the oxidative stability of your polyethylene, for example? So I'm using the DIN ISO 11357/6. So it's the determination of oxidation induction time and oxidation induction temperature. So in this case, both are called OIT. By the way, it's also possible to call the oxidation induction temperature OOT, oxidation onset temperature, and of course the oxidation induction time is the OIT. So in my case, I'm calling, it's easier to understand, I think. The OOT is the temperature and the OIT is the induction time. So what's also possible here, it's written in norm, it's possible to do these investigations under high pressure or under ambient pressure. And what's also important is which crucible do you want to use. So it's possible to use aluminum crucible or a copper crucible, for example. But of course, also the heating rate is important for the onset temperature, and the temperature, the target temperature for the OIT is also really important. So before you start your measurements and your investigations, you really should make sure you have all the information about the samples you will measure here. So let's start with the oxidative stability with the OOT, the oxidation onset temperature. So this is a dynamic test, so we're continuously heating our sample, and through this, that's common practice. We see mostly the melting here, and at a certain temperature, we can see the oxidation. Here on the left, on the right, sorry, you can see a diagram from the norm. By the way, it's flipped upside down. The arrow with the A, exothermic is not going downwards. In our case, the standard setting is exothermic reactions going upwards, but of course you can change it in our software. So you can heat it up with 10 or 20 Kelvin per minute, and also normal air, dried air, or pure oxygen could be used. And yeah, what's important here also for the temperature is the higher the oxidation concentration is, the clearer your signal will get here. So if there's more oxygen, of course, the effect will be start faster and the signal is more clear. And it's the same for the pressure, for example. If you're using high pressure, also here would be more oxidative oxygen at the sample. So it's important to measure under identical conditions for the heating rate in the atmosphere. And as I already mentioned, of course, also the crucible is important because copper is a catalyst for our measurement here. So also here, the measurement could be clearer if you use a copper crucible. So here's now a comparison just for sunflower oil at different heating rates. So I've performed this test with 5 Kelvin per minute, 10 Kelvin per minute, and 20 Kelvin per minute. On one hand, without our OIT adapter, and on the other hand, with our OIT adapter. And what we can see there is with the OIT adapter, the signal is much clearer. Of course, all of them will oxidize at a certain temperature, and this temperature is dependent on the heating rate because, as I mentioned, we were using ambient pressure here. So the pressure is the same. So at the same heating rate, also the onset should be the same, and it's the same. But with our OIT, the signal is much clearer, and there's not so much noise on our signal, and so it's much easier to investigate this. And so this is what we can see here. Here now you can see our OIT adapter. And the thing about this adapter is the atmosphere is exchanged faster. So once you change the atmosphere by a manual gas control or an automatic MFC block, this depends on your device, the gas is directly on your sample and it won't take so long to change it. So as I mentioned, also the pressure is important here and also the crucible. So here you can see now the evaluation for our OOT test. So we are using two tangents here, one at the baseline and one at the intersection of our peak, of our oxidation peak. And so we can see the oxidation quite clearly here. But what's also important, what we can see here, the temperature differs a lot through the different heating rates. So as I mentioned, it's not just the food we want to investigate with our DSC, but also, for example, polymers for our packaging, for food industries, and so on. So just here, one example for LDPE, we can see there also the melting and the intersection at around about 230 degrees Celsius. And what's, for example, common practice is to compare LDPE and HDPE, because they can be separated very clearly through OOT and OIT. Yeah, because the oxidative stability of HDPE is much better than LDPE. And yeah, so this is just an example for the polymer. And what's the difference here in comparison to the last measurement is we were using pure oxygen here. So the onset of our oxidation is really clear in comparison to air, because there's just around about 20% of oxygen inside. So yeah, let's come to oxidative stability, the OIT, the oxidation induction time, or the isothermal oxidation induction time. So we're looking here at the time after which a sample begins to oxidize. So the temperature profile is quite easy. You heat up to a specific temperature. It's, for example, written in the norm for LDPE around about 200 degrees Celsius here, and then you hold it there for a while. And yeah, once your signal is stabilized, yeah, you heated it up, and then you wait for around about 3 up to 5 minutes, and then you can start the oxygen, because the heating is completely under inert atmosphere, for example, nitrogen or something like this, and then you switch it after a certain time to pure oxygen or just air we are using here in this case. So yeah, it's always the same. The higher the oxidation concentration is here, the clearer your signal gets. In this case, for yeah, more realistic conditions, we were using air in our investigations here. And what we've also used is the copper crucible here. So our example in this case are the oils again. So first of all, we compared two sunflower oils, and what we can see there is the onset for our oxidation induction time is really the same. So after 24 minutes, 0.2 or 0.7, the oxidation starts. In comparison to the others like walnut oil or corn oil, there's a huge difference, and the reproducibility is quite good here in this case. But what we also can see there is sometimes no result or no effect is also a good effect. For example, olive oil doesn't react under these ambient conditions in this time at this temperature. Yeah, so this is what we want to prove. So OIT could help to determine the type of oil. For example, if there's no clear separation through the melting behavior here at all. But what's of course also important is the storage temperature and storage conditions at all, as well as the UV radiation, because they will also affect the results. The evaluation, by the way, is quite the same like the oxidation onset temperature. You set one tangent here at a baseline and just one at the intersection or on our peak. So yeah, just to sum it up, what's really important here to receive proper and comparable results is you should choose the really same measurement conditions. So like temperature, like atmosphere, pressure, crucible, and so on. So if you want to compare different samples, it's really necessary to do it in the really same way for your investigation. The reproducibility between the same type of oil, for example, is really good here so far for these sunflower oils. And it's also possible to distinguish different types of oils through OIT. So for quality control or failed path investigations, sometimes also no oxidation like the olive oil could be a desired result. This is totally up to your investigation so far. So of course there are many more. So I think, yeah, if you're into food industries, I think you have so much more ideas what we can measure. So, for example, it's possible to measure honey for the fingerprint of its origin, or you can measure different types of meat for the protein denaturation, and so on. Of course, also, yeah, others like mushroom. What about the moisture and the influence on our mushroom? Or what's missing for today. For example, the CP measurement could be really interesting here. For example, of milk. What about the fat content of my milk and so on. So with ChipDSC, we are mainly using temperature modulation, or we are only using temperature modulation for our CP, so specific heat measurements. And yeah, it's quite works quite well, especially also on a lower temperature range. And what's also possible through the temperature modulation, of course, is to get to know about the reversible or non-reversible parts of your signal. For example, the reversible glass transition or the non-reversible hysteresis peak I was showing in the beginning. So, of course, there are many more. I think, yeah, you have your own ideas what you can measure here. And at all, that's it from my side.